Good day to you. Today we're going to be talking about light, what it is, where it comes from, and some of the things you can do with it. Well, light is one of those fundamental properties of matter. It is a form of electromagnetic radiation. This makes its analysis a little bit complicated and mathematically hairy, but we're going to try to distill down to the essence of what light is, where it comes from, and the kinds of things you can do with it. Well, in order to understand what light is, we have to start with a basic concept of the atom. When we talk about atoms, the Bohr model of atoms, we're talking, of course, about a nucleus surrounded by orbitals in which electrons can reside. And one of the fundamental aspects of that model of the atom is that electrons can exist in various discrete energy states. And so you can have, for example, a ground state where the electron is most likely to be, but then you can have above that, again in discrete layers or levels, various kinds of so-called excitation states where the electron could reside. And normally the electron sits down there in its ground state, and this is the situation at equilibrium. But you can actually come along and put an energy into this atom. And when you put in enough energy, you can actually boost that electron up to another ground state, some higher excitation state. Now, this is not where the electron likes to be. This is not the equilibrium situation. And so there's going to be a natural tendency for that electron to fall out of its excitation state back to the ground state. And when it does, it emits a packet of energy known as a photon. It's not quite a particle, but it does come out in a discrete package. That discrete package is called a quantum. And that is the origin of light. The photon is a carrier of energy that is released when the electron goes from its excited state back down to its ground state. And that, in a nutshell, is the origin of light. Now, there are lots of dimensions to this story for where light comes from. We'll go through some of those, and one of the aspects of it is that the energy that is carried out by the photon depends upon the energy that you put in. Photons cannot disobey the first law of thermodynamics. If you have energy coming out, that means you had to have put a certain amount of energy in, and you can't get more out than you put in, and therefore the relationship between the energy carried out by the photon and the energy in, there's going to be some relationship between those two. Now, if you look at the kinds of things that can cause an electron to jump from one state to another, then there are a variety of different kinds of things that can make an electron do this. One of them is the simple thermal motion of atoms, and this is true for electrons as well. If ever you have any kind of random motion, which is what heat is, then there'll be some tendency of electrons to jump from one ground state to another. But of course, this is a spontaneous process. It's a statistical process. It doesn't happen reliably. It just happens all the time in one form or another, randomly throughout a collection of molecules. And so you can have thermal motion that causes a movement of electrons from one ground state to a fairly low ground state. This is fairly low-grade energy. And when that comes out through here, you're going to get the emission of light, but the light is going to come out in a fairly low energy form. Where on the spectrum this light is going to come out is going to be related to the infrared range of the spectrum that we spoke about in another module. That is that range of light waves that have wavelengths larger than the range of visible wavelength. Now, this thermal radiation, as you would expect, is dependent upon temperature. And of course, if you look at temperature scales, then there are various kinds of temperature scales that are out there. The one that is important for us, of course, is the thermodynamic temperature scale, in which temperature is measured in so-called kelvins. And the Kelvin scale of temperature starts at 0. This 0 is absolute temperature, and of course it goes up as the temperature of something increases. When you get up to a temperature of about 273.15 kelvins, that translates to a temperature of 0 degrees Celsius. Now, the energy that is emitted by this spontaneous movement of photons, or a spontaneous movement of electrons from one ground state to another, this fairly low-grade migration, this is going to happen at any temperature above 0 kelvins. But as you can imagine, the warmer it gets, the more likely this spontaneous jumping of electrons is going to be. And when you get up into temperature ranges that are similar to the kinds of temperature ranges that we experience, that is from 0 degrees Celsius up to about 30 degrees Celsius or so, this is a range from 273 kelvins up to about 303 kelvins down up towards the upper range over here, then you're dealing with an emission of infrared radiation that is actually quite energetic at this level. Now, as you get to higher and higher temperatures, of course, this emission of thermal radiation is going to get to be more and more energetic. This is simply because as you get to higher and higher temperatures, you are prompting larger jumps of the electrons to different excitation states, to higher excitation states. And the energy and light that is emitted in photons is going to be equally energetic. And as you get to hotter and hotter temperatures, then the emission of thermal radiation will get to shorter and shorter wavelengths, higher and higher frequencies, and you'll eventually get up into the visible range. And of course, when you have something that's red hot, of course, that is indicating a certain temperature. When you have something that's white hot, that's indicating a hotter temperature. And if you keep elevating the temperature more and more, you'll eventually start getting into the ultraviolet. This is an important concept in understanding our perception of light, and that is that the light has a certain so-called color temperature, because the frequency of light of thermal radiation that's emitted is determined strongly by the temperature of the object. Now, there are some simple relationships that we can use to actually describe this. One is the so-called Stefan-Boltzmann Law, where we quantify the amount of energy that is emitted, the thermal energy that is emitted, and this is proportional more or less to the temperature in kelvins raised to the 4th power. And so this raising of temperature to the 4th power indicates that the amount of energy that you can get out is very, very strongly determined by temperature. Another law that you can estimate is the so-called Wiens Law, W-I-E-N-S, and this relates the wavelength. Lets you calculate the wavelength according to the color temperature, and this is on the order of about 3,000 divided by the temperature of the object in kelvins. And this comes out in micrometers over here, so 10 to the minus 6 meters, just to make it easy to calculate wavelengths that are in the visible spectrum. Okay, so the emission of light depends fundamentally upon putting energy into a system that enables these electrons to jump from a ground state to an excitation state. And when they fall spontaneously back down to their ground state, that energy has to come out somehow, and it comes out primarily in the form of a photon. And the energy that is carried depends upon the 4th power of the temperature, and the wavelength at which it is emitted is the inverse of the temperature. The hotter the temperature, the shorter the wavelength, the higher the frequency of the light that's coming out. And when we get into very, very hot temperatures, we're talking about emitted light, thermal radiation that is actually visible to our eyes. Now, there are some other things that are important to realize about this model of light generation, and that is anything that you can do to manipulate the ground state of an electron or the energy state of an electron is going to have some impact on the chemistry that is involved with electrons. And of course, all chemistry is simply transfer of electrons. Now, there are a couple of phenomena that are kind of useful to point out here. One is the phenomenon of fluorescence. And in the case of fluorescence, what you have here is you have a ground state and you have a number of excitation states for that electron. And that electron can be made to jump up to another excitation state by energy in. And that energy in can come in either as thermal energy, as we've just discussed, or it can come in the form of a packet of a photon. And so you can have chemicals, atoms or molecules or whatever, that have electrons that are particularly susceptible to being jumped up to another excitation state by the interception of energy in the form of a photon. And when you have that, you have the possibility for the electron to jump back down from its excitation state back down to its ground state. And when it does so, it can release a photon itself. And this is the phenomenon of fluorescence. Quite commonly, the frequency of light coming in will be, there'll be a particular frequency that is especially good at bumping electrons up into another ground state. Remember, frequency is dependent or is related to the energy that a photon can carry. And when that photon is released, when the electron jumps back down to its ground state, that's also going to have a certain frequency. And so you can have chemicals that can absorb light of particular frequencies. Energy comes in the form of a packet of light, a photon that has a certain frequency and therefore a certain energy, and then the energy is released in the form of a photon, oftentimes of a different frequency. And this is the phenomenon of fluorescence in some other of the modules that we've filmed here. We've used fluorescein dye, for example, and fluorescein dye is a very good fluorescent substance. What happens is that a photon coming in that has a fair bit of energy in the ultraviolet range can excite electrons, and the light that's emitted, the photon that's emitted when that electron jumps back down to its ground state, is going to come out at a different frequency, a very bright and vivid green. Now, the fact that you can get photons being absorbed to mobilize electrons means that there's another very interesting thing that light can do, and that is that if you have a ground state, again, and you have a series of excitation states with an electron that can be boosted up to another excitation state. Energy can do that, but also light coming in can do that. So a photon coming in with a certain energy can prompt that elevation of the electron to a new excitation state. And in the case of fluorescence, the electron jumped back down to the ground state and emitted a photon of light. But of course, the basics of chemistry is getting electrons to do things, and one of the ways you get electrons to do things is to enable them to leave a particular chemical bond or an orbital and shift location so that you can change the nature of chemical bonds and the association between different atoms. Now, this ability to capture light energy in a molecule and get it to do work, this is one of the essential parts of the interaction of light with living organisms. Now, the principal ways in which light interacts with living organisms are, one, it can heat them up. This is primarily imparting thermal motion to electrons. The second is it can generate light itself in the case of fluorescence. But the third is that you can absorb light and get it to do useful metabolic work. And the principal ways that that happens is you can either capture light energy to enable you to synthesize a useful chemical. That, of course, is the process of photosynthesis. Or you can use light energy to tell you something about the world around you that is as a form of visual perception. Now, there are certain characteristics of molecules that enable organisms to do this, and one of the characteristics of molecules that interact with light is that they often are very, very complicated molecules. They're not just complicated, but they're complicated in a very specific way. Here, for example, are three forms of chlorophyll that are commonly found amongst plants and other kinds of photosynthetic organisms like protists or bacteria. And you can see from these three different molecules, chlorophyll A and B are primarily molecules that are found in higher plants. There are a number of interesting features to them. The first is that they are quite big, they're quite long. And this zigzag part right here, that's a so-called hydrocarbon chain. But the other thing to note is that there are a lot of so-called double bonds within this molecule. For example, you have a double bond here, 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 here. You have double bonds throughout this ring through here. And one of the properties of chemicals that have lots of double bonds is that these double bonds promote a great deal of mobility of electrons within this molecule. And so what this structure does is it enables this chlorophyll molecule to act essentially as a light antenna. Just the same way that an antenna for a radio can intercept radio waves, these molecules right here can act as light antennas to intercept electromagnetic radiation at the visible part of the electromagnetic spectrum. And so when you have a photon of light coming in and intersecting this, then that generates a great deal of mobility of electrons through these double bonds. And when you have mobile electrons, this means you can have chemical reactions being generated. And this is the basis of the ability of green plants to be able to capture light, to be able to do useful chemical work, the end product of which, of course, is sugars. And there's a very clever way of capturing a virtually unlimited source of energy, that is the light that's streaming into the earth from the sun. And if you have a light antenna that can intercept that light energy, that is tuned to intercept that light energy, then you can mobilize electrons to enable that chemical to participate in useful chemical work. Okay, that's all for today. We'll run into this phenomenon later when we talk about vision, but the basic lesson to take home here is that light is fundamentally a phenomenon of electrons moving around between different excitation states, and when you move electrons, you can get light to power useful chemical work. Okay, that's all for today. We'll see you another time.